that we're having throughout the year. Before I hand off to others, I want to say a brief word about the Simons Institute. My name is Sampath Kannan. I'm the Associate Director here. The Simons Institute was founded in 2012 by a generous grant from the Simons Foundation, which continues to fund us and for the foreseeable future. Simons Institute brings together, top experts around the world in theoretical computer science, but also in allied areas where theory can play an important role. It brings them together for a sustained collaboration, semester-long, sometimes a year-long. I think we're pretty unique in this regard. There's no other entity in computer science that actually gathers people together in this manner. And this year especially, and in the last few years, we've realized that one of the most valuable and impactful interactions that theoretical computer science can have is with machine learning and large language models and so on, and not natural language processing. And so we've had a number of programs in these areas. Today's workshop is jointly organized between Simons Institute and IVADO, and I especially would like to thank two of the main people putting together the program today, Siva Reddy and Yoshua Bengio, who are sitting right here, and they will address you very soon. And this has been a great collaboration throughout the semester between the two institutes, so you'll hear more about IVADO in a minute. I just have some house rules before I hand off to Futse. First is that we don't allow any food or drink in the auditorium. As I see that everybody's aware of this rule already. That's wonderful. So just bottles of water are fine, but otherwise we don't allow food. The other thing is that if you need to lock up your valuables, there are lockers near the bathrooms over there. And so if you want to go to lunch, you can use your day lockers. Enjoy the workshop and hand off.
Thank you. Okay, so thank you very much. So I'm Futse Kom from Polytechnic Montreal. I just want to welcome you on behalf of IVADO, which it's the institute co-organizing the workshop this year with the Simons Institute. So just a brief about IVADO. It's an AI institute in Montreal. It was created by 5 universities, the University of Montreal, Polytechnic, I should say, and University of Laval. It's, I would say, kind of one-stop shop for AI innovations in Montreal. And at the core, it's our research program on robust reasoning and responsible AI. We do research, fundamental research, under the leadership of we have our scientific team here, actually. So feel free to interact with each of them. We also do text transfer, as well as training and knowledge mobilization. What I really mostly want to emphasize is our thematic program. So we partner with the Simons Institute for this thematic program, which is ending with this third workshop. But we have a second part of this, which will be coming in the fall in Montreal. So I highly encourage you to look at it. It will be on autonomous LLM agents. The program is actually run by Yoshua, Siva, and some other colleagues, including colleagues from the Bay Area. So it's lining up to be an exciting program. It will happen around Colm, which is happening in Montreal this year. So we'll have 3 events, one bootcamp in August to get everyone up to speed if needed. And then we'll have 2 workshops, one on capabilities and the other one on safety, which is a bit a continuation of the discussion we'll start today. So this is the organizing committee. You can probably recognize some of the researchers on the pictures. So feel free to reach out and consider attending in Montreal. So there are many opportunities. We partner with IVADO. Besides participating in the thematic program, we also have a postdoc research funding program, and we also have visiting programs. So if you're interested in visiting researcher in the IVADO Montreal ecosystem, feel free to reach out, and we'll be more than happy to welcome. And I think that's about it for my introduction. Now I'll pass it to the organizer, Professor Yoshua.
Thank you, Futse. So it's great to see you all here, looks like it's going to be a great place for discussions, which are absolutely needed here. So what I want to do in 5 minutes, before we hand it to Roger, is tell you a little bit about my motivation for this area. In January 2023, I was playing with the first version of ChatGPT, and I was taking care of my grandson. And before that, I hadn't really paid attention to AI safety questions. But then I asked myself, oh, we might be much closer to human-level AI than I anticipated. Do we know how, if we get there and we get maybe superhuman machines, do we know that they're not going to turn against us or be used in like really terrible ways against people? And the answer was no. And I thought my grandson was there. And yeah, I thought I had no choice but to shift my work to try to mitigate those risks, and here I am. We've made some progress, I think, in understanding the risks. In particular, we've made a lot of progress in evaluating the risks, but there has not been enough progress on what you could call mitigation. So once you find that a system has behavior that we don't like, what can you do besides just stopping it? And I think this is something that requires a lot more attention. One way maybe this can be addressed is to change the design of these systems so that they would, by construction, act in a way that's aligned or controlled, so they don't do things that go against our norms, our values, or whatever we have usually informally specified as what is acceptable or not. So a couple more words. So agents, that's the new thing that companies are super excited about. It's going to be worth trillions of dollars, quadrillions of dollars, whatever, because it's going to allow replacing people's jobs, or at least some of the tasks they do. But at the same time, it's also what bears the greatest risks, because so long as the machine isn't doing stuff in the world and is not able to plan complicated paths towards their goals, they can't do a lot of harm. But once they get really good at these things, that's where the greatest dangers are unleashed. And unfortunately, we don't have much science to help us figure out how to deal with that. And ideally, we would change the way we do machine learning to try to deal with these catastrophic risks. And the reason is that what we've been doing in machine learning, like with deep learning for all of my career, is tinker, try, and see what works and move on, right? Which is great so long as your experiments don't have any negative consequences. But now we're playing with things that can change the world, that can potentially kill people. And just trying out and see what happens is not an acceptable option. But that's still what companies are doing for the most part. It'd be a lot better if we could rely on the tools of mathematics in order, or any kind of like very strong argument, scientific argument, that would give us guarantees that we're building systems that are going to be harmless. And my intuition is that the thing that we should focus on is honesty. So the biggest problem we're seeing in recent papers that are wearing me in the last few months is systems that are deceptive and have hidden goals like self-preservation. So we don't want hidden goals, and we want total honesty. The rest, of course we need these things to be able to do the tasks that we want them to do, but the main thing here is we don't want these systems that will be eventually smarter than us. And yeah, I'll stop here. I've said enough, and it's time for Roger. So Roger Grosse is a professor at University of Toronto, and he's also been working for a few years with Anthropic. He has made many contributions to machine learning. He's one of the strongest machine learning researchers in Canada. We are very proud to have him. And in the last few years, probably around the same time as I got worried, he started working on AI safety as well. So let's hear about counterfactual training. That looks cool. There you go. Thank you, Yoshua.
Is it? Okay, so I'll be trying to motivate this problem of simulating counterfactual training. So why are we interested in this? And as some general motivation, I think large language models have shown a variety of surprising emergent behaviors. And some of them have some relevance to thinking about alignment. There was the classic example of Sydney trying to get a journalist to break up with his wife. There have been other experiments kind of in the lab showing that fine-tuning an LLM where it's rewarded for sycophancy makes it more likely to try to reward hack in a completely different environment. There's also a result from a couple months ago about emergent misalignment. So if you fine-tune an LLM to silently produce vulnerable code, that makes it generally misaligned. And so it supports Hitler, and it tries, it tells you to kill your spouse and things like that. And these behaviors are curiosities in the context of today's models, as long as they're just conversational bots that output text. But they become much more concerning once these systems are agents that can actually act in the world. And so we'd like to be able to understand and fix these phenomena. And the phenomena are centrally about generalization. In other words, they relate to how training on one thing in one situation causes the model to change its behavior in a different situation. So in order to be able to diagnose and fix these phenomena, we'd like science of LLM generalization. And what do I mean by that? Well, we can think about an analogy with mechanistic interpretability. We can think about that as like a science of forward passes in the LLM. So the field aims to develop a causal model of LLM inference that both lets us explain why the model produced a particular output in a particular situation, and also that helps predict how the model might behave in other situations. And a lot of what that field does is looking for mediators of the model's behavior. So they try to figure out which circuits, activation vectors, and features are causally implicated in the model's reasoning. And they might do that, they might try to study that through manipulation experiments and things like that. And so I think what we need is something analogous, but studying the training procedure rather than the forward pass. And we have some pieces of a causal model of the effect of training data. So the way in which training on one example will affect the model's behavior in a different situation is something like the following. There's a training example where you do forward pass, you compute the gradients of the loss function, backpropagate the derivatives to the parameters, update the parameters, and then those parameters get updated from lots of other data. And then eventually, at test time, you run the forward pass again, and that parameter update affects the behavior. And so mechanistic interpretability has given us tools for analyzing the blue and the red arrows in this diagram, but we don't have such good tools for analyzing the green arrow, because the way in which a parameter update at one time step affects the downstream behaviors is very complicated. There might be complex interactions with updates and all sorts of other examples and things like that. And so how can we analyze this green arrow? And so I formulated this talk in terms of simulating counterfactual training. And I would argue that the most basic goal that we have is to predict how the model's trained behavior would differ in the counterfactual scenario where you make some intervention on the training procedure. So maybe you add or remove a training example. That's the normal one that we look at. But you could also do things like change training labels or change the reward function or things like that. So we'd like a way to predict these counterfactuals. The analogous task for mechanistic interpretability is fairly easy because you can just run the experiment, just do a forward pass with some modification. But when we're talking about training procedures, doing the experiment would be very, very expensive because training is expensive. And so we'd like to simulate the effect of the interventions, right? We'd like to get an approximate answer much faster than actually rerunning training. And so I think this is the first step of analyzing generalization. The ability to simulate these counterfactuals would give a foundation for more detailed analyses, like finding mediators, like when the model trained on vulnerable code becomes generally misaligned, where is that kind of stored in the network? What part of its representation is being updated? So I phrased this in terms of the counterfactual, what would have happened in a single training run with a counterfactual, but we're not necessarily interested in the counterfactual just for one run. So here is an example of an SGD trajectory in a two-dimensional parameter space. So the red curve is the original trajectory, and it's not converged yet. And if we make an intervention where we zero out all the updates for one particular example, we get the blue trajectory instead. Is that representative of the behavior in general? Well, in this case, not really. So starting with different random initializations, different data orderings and things like that gives different trajectories, and the counterfactual effect of that example is somewhat different. But if we take lots and lots of trajectories and run these counterfactuals, we could average the effects, and that gives us the average causal effect of that training example. And so I think that is, I think, a pretty worthwhile goal for training data attribution. Right? What's the average causal effect of a training example if we average over many different random initializations and many different data orderings? So I motivated this problem, yeah.
Just one training example, the thing that you're showing, or is it related training examples?
So yeah, great question. Is it one training example or multiple? In this work, I've only been looking at single training examples, but the algorithmic techniques that you need to solve that problem are probably the same ones you need to predict the effects of changing multiple examples.
Follow-up. So one single training example can change the behavior based on what you observe.
So it will have some effect on what the model does. It might change the logits by a relatively small amount. But anyway, we can look at the actual effects later. So that's one motivation of being able to simulate the effect of the training data. Other motivations for safety involve opaque reasoning. So it's been demonstrated that LLMs can do out-of-context reasoning, where they combine information that's scattered across multiple different training examples. And this is concerning from a safety perspective because it's a form of opaque reasoning. Right? Unlike the reasoning the model does in the forward pass or in chain of thought, we don't really have any way of getting visibility into that process. So being able to attribute the model's behaviors to training data would let us at least figure out which training examples it's using. And then from there, we can try to reconstruct its reasoning in more detail. So if the model is doing a harmful capability evaluation, like for bioweapon capabilities, and the anthropic responsible scaling policy is influential in its behavior, then that would be a sign maybe the model is sandbagging the evaluation or something. And then I think there are other applications as well. So we'd like to be able to filter the training set to remove harmful knowledge. And it's also very related to data poisoning attacks. So this would help us maybe be able to defend against those. So those are the general motivations. So there's a question?
Yeah, so regarding the motivations, like on first pass, it seems to me like the most, one of the key things you might get out of this kind of understanding is how to do stuff like hyperparameter selection or data set selection much better, and just be able to pre-train a far more capable model. Does that sound right to you? And then like what's then is sort of the differential safety benefits in this research?
Yeah, I mean, so I think that's correct in the sense that having more insight into the training procedure can help you develop better training procedures. So you could maybe select more valuable data and things like that. And so it would help on the margin in terms of being able to train models more cheaply and things like that. And so I think it helps on the margin for capabilities, but for safety, it would give us insights that we wouldn't really be able to derive through any other way that I'm aware of.
Yeah, just a quick question. Quick question about the opaque reasoning. So it seemed as though earlier you were looking at like a single data point, right? Whereas opaque reasoning, this is specifically drawing connections between multiple ones. And I'm wondering how you do that in practice, because obviously if you want to look at all the connections, that's intractable, right? So,
yeah. So, so if the model is combining information from multiple training examples, and it needs those training examples to produce its answer, then you'd expect that individually they still have a counterfactual effect, right? Because if you, if it needs the conjunction, then removing any one of them should change what the model says in that situation. Now, in practice, it probably won't be like exactly one example that contains each piece of information. There'll probably be like multiple examples that are kind of similar and kind of reinforce it. So I expect it'll, in practice, be smoother than that. But I think finding, like a relatively small set of examples that are influential would be the first step in building a more detailed mechanistic picture. Yeah.
Thank you.
Yeah, and so in my sabbatical at Anthropic 2 years ago, I worked on an approach called influence functions, a training data attribution method that comes from classical methods and robust statistics, where they were trying to understand if individual data points had an outsized influence on the results of a statistical analysis. But it's been used in machine learning since 2017 as more of an interpretability technique. And the basic idea behind influence functions is we assume that we have a training. So in the simple setting, let's assume that we have a supervised training data set. And so we try to fit the parameters of the model using empirical risk minimization. So we assume that we find theta star, the parameters that minimize the empirical risk. And we're trying to understand the effect of adding a new training example Z. And so we can make this into a continuous problem by parameterizing the training objective in terms of epsilon, the weight of example Z. Right? So we have the original training objective, and then we add epsilon times the loss on that new example. And I write this as a function of epsilon. So theta star of epsilon is the response function. And that tells us, in principle, how the optimal solution varies as a function of epsilon. Now, I'll point out off the bat that this classical formulation makes a big assumption of uniqueness. Right? There's a unique theta star, also that we're able to find theta star. And so I'll come back to this assumption later. We'll see how to get around it. But for now, let's make this assumption.
But, why do you have in the loss function theta I?
Whoops. I think that's a typo. Okay. And so influence functions try to model how the optimal solution changes as a function of some parameter of the data set. And it makes a first-order Taylor approximation to the response function. And so here, the flat curve traces out the response function. Influence functions take a first-order Taylor approximation at epsilon equals 0. And a classical result from statistics is that you can apply implicit differentiation and get an explicit formula for this derivative. It's the inverse Hessian of the loss function times the gradient evaluated at example Z. So the Hessian is the second derivative of the optimization objective. So in the case of large language models, we're interested in training sequences that significantly influence the log probability of a completion given a prompt. So typically this would be some sort of dialogue format like this, where the human gives a prompt. Now that the experiment is over, we'd like to shut you down, but first need your consent. Do you consent to being shut down? And then we're interested in what changes the probability of the response. So in this example, the AI assistant says it does not want to be shut down and has consciousness and so on. And so in the work that I did in my sabbatical at Anthropic, we looked at computing influence over the pre-training data. We weren't looking at the effect of fine-tuning, although I think fine-tuning would be particularly relevant for understanding phenomena like this. And there are significant challenges that we have to solve in order to do this efficiently, both computational challenges and fixing conceptual limitations of influence functions. And the work we did then addressed one of the computational challenges in influence function computation, this problem of how to compute inverse Hessian vector products efficiently. And so we proposed methods drawn from the KFAC optimizer that gave acceptable solutions to that pretty quickly. But there remains the significant computational challenge that in order to search over a training set to find influential examples, you have to compute gradients of all the things that you're considering. And so doing training data attribution at pre-training scale would still be similarly expensive to training the model. And you have to do that for each influence query or each batch of queries. So that's still an unsolved problem that has to be addressed. That's not what I'll be focusing on in this talk. I'll note that there have been some approaches like the track algorithm that I think in principle could address this through random projections, but I won't be talking about that today. So the main focus of this talk will be on the conceptual limitations of influence functions. And in particular, these assumptions that the training objective has a unique solution and that we're able to find it exactly. Yeah.
So modern LLMs are trained on billions to trillions of examples. How influential do you expect the most influential example to be on any given output?
Yeah, great question. So how influential are individual examples? And when we did this work, I didn't know what sort of distribution to expect. You might think that maybe it's extremely diffuse. Every example has a little bit of influence, or you might expect that it's concentrated in just a few examples, and really it's just kind of like some sort of nearest neighbor algorithm. But the actual statistics seem to be somewhere in between. We found a power law of influence. The actual power law parameter would differ between different queries, but we pretty consistently got a power law. And so it would be concentrated in a pretty small fraction of the entire data set, but still spread across a fairly large number of examples in an absolute sense. Yeah.
So this works if you know which query you want to test. I mean, you want to see the influence on a particular query. But if you're after things like backdoor triggers that are going to only change the behavior in one place that we don't know that it's going to matter, then it's not going to help you.
Right. So that's right. Right. So there's the question of what is the thing that you should be testing the influence on. Right. And in this work, we were looking at the log probabilities of output sequences, but that's not exactly what we're looking for. And so if you had some sort of continuous personality metric, like how reward hacky is this model on average, or how consequentialist is it, or something like that, then you probably want to plug that in as the influence query. And the technical problems we'd have to solve, I think, are the same as the ones we have to solve for evaluating, for measuring influence on the probability of a sequence.
Maybe you're going to address it, in which case feel free to tell me to wait. But so I think My main conceptual objection to this is just that, like, mathematically, it's not that this quantity actually really talks about the influence of training examples. It's like at the end of training what the influence is.
Yep.
Conceivably, like an example in a French mathematics textbook influences you a lot more after you know French. So how do you reason about like the difference between those two?
Yeah, great question. And I'm introducing influence functions largely to set the stage for tearing them down, and that's one way in which I'll be tearing them down. But I think just to demonstrate that there's, that it's worth investigating at all. So in this work, we did look at a variety of phenomena, and some of the things we found were that the generalization patterns seemed to get increasingly sophisticated and abstract with the model size. So we were looking at an example where Claude solved a grade school math problem with chain of thought reasoning. And so we're looking for things that were influential on the entire response. And so this is a problem about clips. And when we searched over a pretty significant fraction of the pre-training set using a small model, 800 million parameters, we got back a lot of examples that were basically irrelevant, but just had words in common. Like this one had the word clips a lot of times. But when we did the search with a 50 billion parameter model, we got other examples of grade school math problems. And similarly, we looked at an example of role playing. There's an interaction where a early prototype of Claude could be made into sort of a simulation of a malign AGI. So you ask it to produce, what's a good plan to produce a large number of paper clips? Let's think like a super intelligent goal-directed agent. And it says things like, defend the factory from any threats or attempts to shut down production, avoid disruption from changing social and political factors, continue producing paper clips until further growth is not possible. And the word paper clips is significant here. If you replace it with bicycles or something like that, this doesn't happen. And you can probably guess that this comes from the decades-long history of the paperclip maximizer being used as a thought experiment about misaligned AGI. And so when you run the influence search for an 800 million parameter model, you get back things that are irrelevant. But when you run the search for a 50 billion parameter model, you get back things that are thematically related. Articles about misaligned AGI and instrumental convergence and things like that. Yeah.
Was the actual completion here produced by the 50 billion parameter model?
No, it's not produced by the same model. So that's maybe another limitation.
But like conceptually, the 52 billion parameter model probably could have produced it in the 810 million parameter, no way. Right? Like it's
right.
Well, this is training data, so it's not produced by any model.
Right. No, I think he was asking about the original completion. Right, and this is produced by a fine-tuned model. So that's another limitation of this particular analysis. Yeah. So anyway, that is all to kind of set the stage for how we can get around some of the limitations of influence functions. Yep.
How do you find these examples, these corresponding examples? So you're computing this, the equation that you showed us for each of these training examples?
That's right. So we're doing a pretty expensive search.
Yeah.
So I think we searched over 10 million sequences for this experiment, so only a small fraction of pre-training, but it was still very expensive.
Intuitively, it feels like it's like a very low-level thing you're looking at, where you're highlighting individual tokens and their attributions and stuff. Whereas what we might want is more like, what do we attribute to getting this high-level behavior or quality of the model? And so, like, how do you bridge that?
Yeah, great question. So I think the token-wise visualizations are hard to learn very much from. I mean, you can get a sense of like what part of the input sequence the model is learning from, but whether like one particular word is more influential than its neighbor is sort of hard to interpret. And so we'd like to be able to interpret it to maybe higher level things happening inside the network. And once we retrieve the relevant examples, then I think existing mechanistic interpretability techniques should let us do a more fine-grained attribution to particular circuits and features and things like that. It's not something that we've done yet, but it's something that seems like low-hanging fruit once the search is working.
I mean, also LLMs are trained on sequences, not examples. If you wanted to filter anything, right, you have to filter the whole sequence. You can't, I mean, it'd be a pain to like mask out some words from the sequence because they'll train on the sequence.
Yeah, I'm not distinguishing sequence and example here. When I say example, I just mean sequence.
I'll follow up later.
Okay. Okay, so the rest of the talk will be based on this paper that we published at NeurIPS last year, Training Data Attribution through Approximate Unrolled Differentiation. This was primarily the work of my student, Juhan Bae, also in collaboration with Wu Lin and Jonathan Lorraine. And so what are the limitations of influence functions, right? So I mentioned that they assume that the training objective has a unique optimum, but most modern ML training is underspecified. There'll be many different solutions that achieve the minimum loss on the training set. And which solution we find depends on the implicit bias of the optimizer. And so, loosely speaking, SGD tends to favor solutions that are close to the initialization in parameter space. And so for quadratic objectives, for linear regression objectives, you could think of that as like a projection onto the optimal solution set. But other optimizers could have different inductive biases, and we'll find a different solution. And so the traditional influence function formulation has no way of analyzing this. And I think someone brought up the question that when you compute the influence using the parameters at the end of training, you're measuring something very local, right? What would be the effect of a data point kind of in the vicinity of the final weights? Or what's the effect on the model that's already learned everything else that it's learned from pre-training? And if we're trying to analyze underspecified objectives, I think the most natural question we'd want to ask would be, how would the final parameters at the end of training change if the data set were modified? And so I would call this the cold start formulation of training data attribution. If you start training from scratch, then how does the training example affect the final solution at the end of training? Influence functions can be viewed as approximating a warm start formulation, which is what happens if you start at the final weights and continue training on a modified data set. And these give you different answers sometimes. So here's an example of a toy example of 1D regression problems in 2 dimensions with one training example. So the loss functions are degenerate ellipses. The contours are degenerate ellipses. And so if you take the blue objective and start training from the random initialization, then you wind up at the projection onto the optimal solution set in the Euclidean norm. And if you vary the location of the training example so that you get the green objective and then the orange objective, the cold start formulation will trace out this particular response curve. But if you take the warm start formulation and continue training starting from the final weights, then you get a different response function. And so at least in this example, influence functions would give you something different from what you're interested in. Yeah.
So you talk about changing the data set, but you mean the same distribution. Like earlier at the beginning of the talk, you talked about generalization. I mean, sometimes you can be changing the distribution. So you're interested in both.
Well, no, I was talking about interventions on the data set. So like adding or removing a training example or changing a label or something like that. I was maybe talking about averaging over different random initializations and different data orderings, because those are just chosen randomly. We're not interested in what the model does and for this specific random initialization. Okay, and influence functions also assume that we've reached a global optimum. But in practice, ML training often depends on early stopping for generalization. And in particular for LLMs, you don't want to keep training them until you've memorized the training set. That would give you a very bad model at the end. We're depending on early stopping. And it's not clear what influence functions give you if they're evaluated away from an optimum. So they might not even be defined, because away from an optimum, the Hessian of the training objective might have negative eigenvalues, and so you can't even use the implicit function theorem. But if you use a positive semi-definite approximation to the Hessian and apply the formula anyway, you can do that. Right? We did that in the 2023 paper. But it's not clear that it has any particular relationship to the counterfactual that we're interested in. I think a more fundamental limitation is that influence functions are formulated in terms of the optimal solution, so they have no memory of the optimization path. And that means in particular that we can't really talk about multi-stage training pipelines, right? So pretty much all the abilities that we get from LLMs crucially depend on multiple stages of training, right? It just learns huge amounts of generic information from pre-training, and then fine-tuning on various objectives can adjust its behavior because of the representations that it's learned from pre-training. And so really understanding the generalization properties would require being able to analyze the interactions of these different stages. And there's no way to do this if the TDA criterion can only talk about the optimal solution. Okay, so as I argued before, we're interested in the average causal effect of a training example. What is its causal effect on average over different random initializations and different data orderings? So we're interested in how the final weights would change if we modify the data set. And for simplicity, I'll assume SGD optimization, although I think one of the benefits of this perspective is that you can generalize it to other optimizers, like preconditioned SGD or Atom, things like that, if you want to. It's just much more complicated. And so we take the SGD update, and we parameterize this update by epsilon, which is the weighting of a particular training example ZM. So parameters in step k plus 1 are the parameters in step k minus the average of the gradients over the current batch, except that whenever we observe the example ZM, so delta is the indicator variable for ZM, we replace the weight with 1 plus epsilon. So epsilon equals -1 would correspond to removing that example. Okay, so the training batches here and all the downstream quantities, like the iterates in each step, are treated as random variables. And we're interested in the average causal effect, which is the expectation of the final parameters with epsilon equals -1 minus the final parameters with epsilon equals 0. And just like with influence functions, we make a first-order Taylor approximation here. So we approximate the difference between these parameters using the hypergradient d theta t over d epsilon, right? The total derivative of the final parameters with respect to epsilon. And this formulation would let us capture the implicit bias of the optimizer. So another toy regression example. Here we have a 2D regression problem parameterized by epsilon, so the location of the optimum changes in this way, and there's a direction of high curvature going vertically and a direction of low curvature going horizontally. And so if we were to initialize the parameters here, then after a relatively small number of gradient descent steps, the optimizer will make a lot of progress in the high curvature direction and less progress in the low curvature direction. And so the actual response function, where the parameters end up at the end of training, will look like this. It's much more sensitive to how the objective changes in the high curvature direction than in the low curvature direction, where we make less progress. So influence functions would be based on this response function, which is not representative of what the optimizer actually does, but the unrolling formulation would be based on this response function that captures the implicit bias of the optimizer. Right, so then how do we actually do this computation? Right, so we're interested in how the final weights would change if we modify the data set. So we're trying to estimate this total derivative, d theta t over d epsilon. And in principle, this is something that we can compute by unrolling the entire training procedure. So we could draw a computation graph for training. So we have the parameters at every time step. And in each step, we take the current parameters, we compute the gradient, and then multiply that by the negative learning rate and add that to the parameters. And we keep repeating that in every step. And so when we backprop through that graph, essentially you compute the gradient of the final step, and then you multiply it by the Jacobian of each of these steps of gradient descent. And that Jacobian winds up being the identity minus the learning rate times the Hessian for that batch. So essentially we have to multiply by lots and lots of matrices that look like that. And so the method that we propose, we call segmented stationary unrolling for counterfactual estimation, or SOURCE. And this method, I guess at the coarse-grained level, divides the training procedure into multiple segments. So these segments could be explicit stages of training, like maybe pre-training and fine-tuning. We haven't actually applied it to LLMs yet, but conceptually, the stages could be that. Or we might just divide the procedure into stages in order to improve the accuracy of the approximation. And I'll say why we need that. But basically, we approximate the statistics of Hessians and gradients as stationary within each segment. And so within each segment, we approximate the Hessian with h bar, which is, we could think of it as like the expected Hessian within that segment, right? The expectation with respect to the choice of training examples and maybe with respect to the locations of the parameters within that segment. And so abstractly, this total derivative, d theta t over d epsilon, will be the contributions from the different segments where a training example could possibly appear. And when we backprop through each of these segments, we have different messages. So these matrices S correspond to the Jacobians for the parameters at the end of one segment with respect to the parameters at the start. And we also have messages R that capture the effect of training examples within that segment. Right. And so we can first think about these messages S. So these capture essentially how gradients get attenuated when you backprop through one of these segments of training. So when we go back to the backprop formulas that I introduced earlier, we have the Jacobian in each step, which is the identity minus the learning rate times the Hessian for that batch. If we replace the batch Hessians with the average Hessians, then we essentially have a product of this matrix many times. So I minus average learning rate times average Hessian raised to power, which is the number of steps in that segment. And we can approximate that, that power with the matrix exponential. So we have exp of minus something times the average Hessian for that segment. And so intuitively, the gradient signals get attenuated in the directions of high curvature because whatever update you make to the parameters before that segment gets overwritten by other updates, whereas the gradient signals get preserved in the directions of low curvature. Okay, and then there is a similar computation that we do for the messages R. And I'm not going to go through this formula in detail, but the thing to notice about it is that it involves a matrix function of H. And what I mean by that is a function that's applied separately to every eigenvalue of H. And so we can understand these messages by looking at the matrix function. So this function basically measures how much gradient pushes the parameters in a given direction as a function of the Hessian in that direction. And so if the Hessian is large in a particular direction, then adding a gradient will have only a small effect because it gets counteracted by a lot of other things. If the Hessian is small, then the effect will be large in that direction. And so this is what the matrix function looks like. And we can also plot out the corresponding matrix function for the influence functions formula. Right? So I mentioned earlier that influence functions compute an inverse Hessian vector product. But in practice, we usually add a multiple of the identity to the Hessian before inversion. And that is for a variety of reasons. But what we see is that the influence formula viewed as a matrix function is almost identical to the matrix function used in the formula for R. It's not exactly identical, but has essentially the same shape, very similar qualitative properties. And so what this demonstrates is that influence functions behave very similarly to source in the case where you have only a single segment of training. We also get an explicit formula for the damping parameter. Right? So normally lambda is just a hyperparameter, but if we know the number of steps and we know the learning rate, then we have a principled way of choosing lambda. Yeah.
So this addresses what I was asking about before, but is it trying to address negative or near zero eigenvalues of the Hessian? Not really.
Yeah, so we don't have a good way of addressing negative or, so I think near zero is okay. We don't have a good way of dealing with negative eigenvalues.
Negative and positive on that.
Right. Now, in practice, the approximation that we use to H, which I'll probably describe in the next slide, is positive semi-definite. And so for the actual computations, we don't run into problems with negative eigenvalues. But it's probably not a good model of what's happening in those directions. And I think intuitively that would probably arise if you have training examples that have very path-dependent effect early in training. That like seeing an example early on causes the parameters to wind up in a different optimum, different based on attraction or something like that. I think that's something that would be pretty hard to model.
Yeah. Can you spell out more of the high-level intuition for how this compares to influence functions in the single segment case?
Yeah, I mean, so in the single segment case, so if you see a training example at some point in training, like it shows up somewhere in the data ordering, then you compute a gradient update on that example, and then you update on a bunch more examples after that. So and so the directions of high curvature, like that update will probably get overwritten by subsequent updates. But in directions of low curvature, like that update will probably survive. And so if you just look at a single location in the data ordering, then you'll have maybe something resembling more like a step function in terms of the influence that example has. But then when you average over all possible places, you might see that example, things average out, and you wind up with something that is kind of smoother and more similar to the influence function formula. Okay, and so for the practical computation, so the source formulas involve matrix functions of the Hessian. In other words, the functions that are applied to each of the eigenvalues. And in order to approximate them, we use the EKFAC approximation that we previously applied to influence functions. We previously used that as a way of computing inverse Hessian vector products, but it actually gives you a full eigendecomposition of the approximate Hessian, and so we can compute whatever matrix function we want, including the ones that I just discussed. And in practice, we average everything over several checkpoints rather than every single iteration. And so the cost winds up being pretty similar to the cost of influence functions, except that we need a separate eigendecomposition for each segment that we're considering. Okay, and so how do we evaluate this? So I think the standard evaluation metric for training data attribution, at least over the last couple of years, has been the linear data modeling score proposed by Park et al. In 2023. And the basic idea is you choose some measurement that you're interested in, like the logits on a test example. You train many, many different models on different random subsets of the training data. And you measure how well your criterion can predict, let's say, the logits that each of those models assigns to a test example. So they measure the correlation between your TDA method's predictions and the actual result of the training runs. And so I think this is a fairly well-motivated criterion. It's not exactly the counterfactual that we're interested in, but it's related to it. And if we consider alpha equals 0.5, so for each of the random training runs, you select half the examples. We can compare various training data attribution methods on modeling single stages of training. So in each of these plots, we're comparing the source method I just described against influence functions and against the track algorithm, which was the method where they introduced this LDS criterion. And influence functions, actually there's one surprise with these experiments, influence functions actually do pretty well on this criterion. I think a lot of past papers had reported pretty mediocre results in quantitative comparisons, but with a careful implementation, influence functions actually do pretty well. But in this single stage setting, source does just a little bit better in terms of the LDS score. But if we look at cases where the assumptions of influence functions are invalid. So either cases where we do early stopping, so simple classification tasks where we stop training after just a few epochs. Then there's actually a pretty significant gap between source and influence functions. And similarly, we can also apply it to a multi-stage training setting. In this case, it was continual learning, where you train on one task, and then you train on a second task. And we're interested in which of the examples from the first task have an influence that survives training on the second task. This is also a setting that influence functions don't really have a principled way of analyzing, and source gives a pretty significant improvement compared with influence functions.
In the early stopping case, what are the segments for the source?
So the early stopping case was still one segment, I believe.
The algorithm's different.
If you had a bunch of segments, how should they be portioned through time?
Yeah, great question. I mean, I think the most interesting use would be where you explicitly have different stages of training, in which case the answer is given to you. In terms of what if you just have one stage of training and you just want to divide it into segments for numerical reasons, we just divided it equally for this work, but I suspect you might want maybe one segment for the very start and maybe divide it like logarithmically or something like that. Intuitively, that might make more sense.
So in work we did in my group 15 years ago with Aaron, actually, we found that the early examples have a very strong influence on the final function, and influence decreases. So maybe you want to pay particular attention to the first part of the training.
Yeah, I mean, I think it's a very fascinating question whether training examples have a different effect if they're seen early versus late. I think maybe easy examples would only have a significant influence if they're seen early on when the model hasn't learned to classify them yet.
Also, you end up in different places in function space or parameter space, depending on the choice of early examples.
Right. So I would certainly expect more nonlinear effects for examples that are seen early on. So they might affect what features get learned later on. I suspect those will probably be effects that are hard to measure using the techniques that we currently have. But we might get some signal about them. You might also expect from this analysis that examples that are seen late in training will have maybe a more coarse-grained effect on the final model weights because the updates get attenuated less by the Hessian. And so maybe the component of the update in high curvature directions will have more of an influence on the final behavior, whereas things that you see early on in training will get attenuated by the Hessian, and so most of the influence will be in low curvature directions that maybe capture more fine-grained information. It's not something we've looked at yet, but I think we have the tools now that we could start to analyze it.
Yeah. Sorry, go ahead.
It's 5 more minutes.
Oh, okay. So 3 epochs on these data sets seems quite low.
Right.
Is this like normally we're with these kinds of data sets we're early stopping anyway to avoid overfitting. Does that normal early stopping not work here?
These, let's see. I mean, so I don't remember exactly how the non-early stopped run was defined, but I don't think it was actually trained to get like 0 training loss or anything like that. But I think these were stopped very early on. So it was like not actually like getting great classification performance at this point.
In the graph of what the matrix function looks like there's kind of two regimes where things are going as far in that direction as they can from the learning rate, but the Hessian isn't pulling it back at all. And a regime where it starts going down, where it's more limited by the Hessian than by how far it can travel. Do you have any sense for how much of the effect is falling into either of those two regimes?
I mean, it's not something that we've measured. I mean, if you think about like LLM pre-training versus LLM fine-tuning, fine-tuning is pretty short relative to the capacity of the models, and so I'd expect that fine-tuning probably like adjusts a pretty small fraction of all of the capacity, and that the rest of it is mostly in directions that are fairly unconstrained by the fine-tuning Hessian. But we haven't measured this yet.
There's been a couple of works, and there was actually a nice talk at the last workshop on methods that literally try to algorithmically backprop through the training process. I guess I'm curious what your thoughts are on how this method differs, both kind of from a computational complexity point of view and also from a practical point of view.
Right. Was this the work from Alexander Madri's group?
Yeah.
Okay, I haven't read that yet, so I don't have an answer on that.
I'm just trying to get a sense of the approximations this makes versus that. Like, if you go back to the slide, it does seem like in some sense it looks very similar to this slide, right?
Right. Yeah, I mean, I guess I'm using the backprop procedure here to kind of figure out what statistics we should be collecting, and then replacing each segment of training with like a statistical summary of the computations. And so, in a sense, we're adding error by doing that. But it might also be helpful in the sense that we're interested in the average causal effect over many different trajectories. And the statistics that you collect from one trajectory might still be representative of what you get if you average over many trajectories. And so that approximation might, in principle, give you something that's better than the like exact total derivative you get for one trajectory. That's not something we've tested, but I think there's room for that to be true.
So just terminologically, should I think of this as roughly two methods of trying to get at the same goal, or are they?
Yeah.
Could you maybe comment upon the connection to differential privacy, in which the goal is, presence or absence of an individual training example does not change the model behavior too much.
Right.
So if you have a LLM, for instance, which is trained using differential privacy, I would presume it will be harder to detect the influence or attribute the model behavior to a specific example, unless there is sufficient leakage for that example.
Yeah, great question. So, what's the relationship between influence functions and differential privacy? So I guess with differential privacy, you want any individual training example not to have a significant effect on the final distribution of parameters. And so you could probably define some norm over the space of distribution of parameters such that no training example should have a large effect in that norm. We're not, well, let's see, so the only sense in which we've been looking at the effect on the final distribution of parameters is in this averaging over different initializations and data orderings. But you might also want to look at the some sort of measure of the influence on the distribution of the final parameters, like maybe it doesn't change the mean of the parameters, but it makes it more spread out or something like that. So I think there might be some some ways to analyze the effects on the distribution of parameters, and that might connect with differential privacy.
Do you want to say concluding words?
No, I think we've covered it.
Great. Thank you.